Thanks a lot to the organizers for inviting me very last minute. Hope I can live up to the expectations you have for the original speaker. So today the topic of our discussion is excitonic quantum criticality. And this is joint work with Hart Goldman, who's in the audience and going to Minnesota next year, and Zhu Huan, who is my office mate at MIT, whom I enjoyed talking to a lot, and of course, Sento. So these are based on these two papers. One is this single author paper from last year, which is more technology development. And then we had a paper earlier this year which focuses on this excitonic quantum criticality in a metallic environment. So without further ado, let me just dive in. I really shouldn't be talking about this because I'm not an experimentalist, but I'm just showing you the classic plots, the earliest plots from Maré twisted bilayer graphene as an illustration for the gift that we're receiving from all these strongly tunable 2D materials. So I want to emphasize strong tunability because that will be important for the phase transitions we want to explore later. And as you can see in this phase diagram, you can have almost continuous tuning of carrier density, and you can also tune the twist angle in the system, which is not shown here. And in these experiments more recently, we also saw that displacement field tuning can give you an interesting knob to change the bandwidth and the competition between kinetic energy and interaction energy. So I really want to emphasize that this is not just the ideal for precision study of novel phases, but also for exotic phase transitions. So from the last couple of days of the conference, we've seen that exotic phases really exist. In particular, these fractional quantum anomalous Hall phases have been observed both in twisted MOTE2 as well as in pentalayer graphene. And we also have some suggestion of a possible fractional quantum spin Hall effect from the Cornell group. So I'm sure the list will keep growing. Okay, but one thing I want to emphasize is that so far we've been excited about these exotic insulating states, which might have topological order. But metallic states are by far the more common fate that you would encounter a generic filling as you go around and explore the phase diagram. So I want to emphasize that I don't think metals are boring, although people almost never mention them in the phase diagram. And in fact, in these in some of the graphene system, there are a huge variety of very interesting symmetry breaking Fermi liquids arising from flavor polarization. So you can imagine in these systems you have some spin, some valley, or other internal degrees of freedom, which and there's some symmetry which preserve their quantum numbers, but these symmetries are spontaneously broken as you tune through the phase diagram of some of these 2D materials. So this is just one example in trilayer graphene. So unfortunately, so far, the transitions that experimentalists observe appear to be first order. So sort of doing theory, if you see a first order transition, you should just give up. But so we want to really ask, is there a possibility of having a metallic continuous quantum phase transition in this space of flavor polarization, spontaneous symmetry breaking? So this is the guiding theoretical question. Can we find a clean 2D non-Fermi liquid at a flavor symmetry breaking transition where two of the following properties hold? So the first thing is that we want to make sure that fluctuations do not destabilize the continuous transition. So this is non-trivial because as we learned from, Halpern, Lubensky, and Ma many, many decades ago, it's possible for a fluctuation effect to destabilize a mean field second order transition and give you a first order transition. So I want to see how that can be avoided. And the second thing is, can we access the critical properties of these metallic critical points in the direct transport measurements, which are the most accessible in these 2D materials? So this question is also non-trivial, as Subir already mentioned in his talk, because this is hard to access in a single flavor metallic quantum critical points due to some non-perturbative constraints that I will mention as I go along. So guided by these two questions, let me come to our partial answer. So of course, this is not a only example. I'm sure there are many examples you can come up with, but this is the simplest, and this is called excitonic quantum criticality. And because there's some confusion in the language of excitons, I want to clarify it in the beginning. So what we're considering is we have two flavors of degenerate Fermi surfaces. They could be related by, say, depending on your specific setup. If your flavor is spin, this is a different spin species or valley species layer. Take your favorite one. And we want to break the spontaneously break the relative U1 symmetry that rotates the two species. So in other words, we condense this exciton, the C1 dagger C2. So at this, in different setups, people have different names for this. If it's spin, it's called XY ferromagnet. And sometimes in Maré, people talk about intervalley coherence. So I'll just treat this general set of phenomenon. But the key point is that these excitons are in a metallic environment. So they're not insulating excitons. So, okay, what are our main results? So before we answer the two guiding questions, I'll first give you some general theoretical developments that we've been able to achieve to refine and extend some controlled expansion for a metallic quantum critical point. And then we'll use this particular expansion to answer these questions, and we will show that indeed continuous transitions can survive, and we have a very simple counterflow transport probe that is sensitive to the dynamical critical exponent at the metallic critical point. So here is an illustration if you take the flavor index to be layer, then this counterflow is easily understood by driving these equal and opposite currents in the opposite layers. Okay, so now let's go to the more detailed parts. So I'll begin with some general framework for non-Fermi liquids, and we'll talk about the controlled expansion as a technology development, and then I'll discuss the two properties that I promised. Okay, general framework. So what is Hertzsmillis-Morea? So this is a general description of lambda ordering transitions in a metallic environment, and sometimes this is called a minimal model of non-Fermi liquid physics. And the basic picture is very simple. You take some Fermi surface, you take a bilinear operators of the fermions, and they could carry some flavor indices, they could be some form factors, but generally they're coupled to this Gapless boson, which is undergoing a standard Landau transition in a given symmetry class. So the Landau action for the boson, we'll keep the quadratic piece here, and I will keep the momentum dependence of the boson dispersion in general. The standard choice here is, of course, z equals 2, where you just have the gradient square coupling for the Landau action. But we'll see why this will be useful later. So we can, of course, think about the mean field phase diagram of this theory. So I take this Landau action, and I can tune the mass of the boson. So if the boson is massive, I can just integrate it out. It doesn't really affect the Fermi surface. It only leads to short-range interactions. When the boson condenses, we get a symmetry-broken Fermi liquid, and we just have a simple quantum critical point in the middle. However, there are singular IR fluctuations in this theory, which ruin this simple mean field picture. The simple way to say this is that the Yukawa coupling that you add to the decoupled theory is strongly relevant on the renormalization group flow, which means that the decoupled theory is not really a good perturbative starting point. You need some alternative expansion to really study the theory in the infrared limit. So what expansion can we seek? The simplest expansion that we've heard about already a few times in this conference is the ordinary large N expansion, where you change the fermionic part of the action. So let's look at the red part. From one single fermion flavor labeled by C to this n different fermion flavors. And you don't change the Landau action for the boson. And in the interaction term, you also couple the Landau boson to this sum over I of C dagger ICI. Again, I emphasize that there can be additional flavor indices in this fermion bilinear that I'm suppressing. Crucially, you have this 1 over a square root n factor, which will suppress the fluctuations in the large N limit. So, okay, you can go ahead and just calculate it, right? This works very well for, say, Dirac quantum criticality, where you don't have a Fermi surface. And what you find is that, okay, the self-energy is 1 over n times omega to the 2/3, which is much more singular than the bare energy, which is linear in omega. And then you get this Landau damping for the boson, which is very familiar already in Fermi liquid theory. But large N is not enough, okay? As Sansek taught us in 2009, and also I think Zhen also mentioned it during his talk in a different guise, this 1 over n suppression, although you have a 1 over n suppression, the dependence on frequency is so singular that when you do higher loop calculations, it becomes, the factor of n gets moved to the numerator. And therefore, higher order diagrams will actually get enhanced by additional powers of n. And this will ruin the naive combinatorial counting that you can get by just looking at the loops in the sums over internal indices. So this proliferation of loops means that the theory actually is at least as complicated as planar SU engaged theory, which I will certainly not be trying to solve in this talk. Yeah, so we want to have some alternative scheme that's more amenable to analytic analysis. So an improved double expansion was proposed by David Moross and friends in 2010. And in addition to having n-fermion flavors, you change the dynamical critical exponent of the boson from z equals 3 to z equals 2 plus epsilon. So now let's look at the blue part of the action, which is the only part that's modified from the previous page. You have this q to the 1 plus epsilon, which is sort of a non-analytic term. So this non-analyticity might bother some people, but let me just remind you that this famously appears in the HLR theory for composite Fermi liquids, where this epsilon is actually equal to 0. So now we can try to do this modified expansion, where we take n to be large and we take epsilon to be small, but with epsilon times n fixed. Okay, so if you do this, then we can ask what saves us from the trouble with the ordinary large n expansion. And what saves you is that you get a factor of epsilon in the denominator as well. So n gets replaced by n epsilon. So long as you keep n epsilon fixed, this is not as, you don't get additional powers of n when you calculate higher order diagrams. So there's a subtlety here, which is, some friends from Perimeter in 2021 found a possible for-loop divergence. Okay, some very, very complicated effect. So I will not address these because that will not address our results at 3-loop. Yes, please.
Sorry, so what is the statement? If you put small epsilon terms that would not
Yeah, so for small epsilon, if you look at this expression, the prefactor is 1 over n epsilon rather than 1 over n. So that means that there is no, even if you flip it to the numerator, it's just the order 1 number, because I'm keeping the product epsilon n fixed and taking n to infinity. So it's a different kind of large n expansion.
Sorry, but without epsilon, there were other terms that were 1 over n that you had to resolve, right? And now you...
Yeah, well, without epsilon, even if we just focus on the first term, this 1 over n times omega to the 2/3, that's much more singular than the bare dispersion or the bare electron Green's function. So in the IR limit, if you put it in the denominator of your Green's function, this 1 over n then gets moved to the numerator, which means that higher loop diagrams will pick up factors of n in the numerator, and that will ruin the counting for the 1 over n expansion. Yeah. Okay, so modulo this subtlety, let's proceed and see how far this expansion can take us. So the first question, right, we want to address is the continuity of this metallic quantum phase transition. So we know that gapless fermions from this huge, infinite number of gapless degrees of freedom living on the Fermi surface can give rise to singular corrections in the boson action. And this can trigger a fluctuation-induced first-order transition. So there's some old results reviewed in this very nice review article by Belitz and friends that says that if you approach from the Fermi liquid side, right, where the correlation length C of R is finite, but you take the correlation length to be larger and larger, you can compute the boson self-energy generated by the virtual fermion fluctuations. And you find that there is a singular negative correction, right, which is proportional to the absolute value of Q. So if you imagine looking at this expression, and if the singular negative Q survives right at the critical point, that means your critical point has a negative direction, and the original critical point that you started with at the mean field level is unstable. So we don't want this to happen, right? But there's a caveat, right, which is this analysis, technically, at the critical point, we don't know what happens, because the correlation length also diverges at the critical point. So really, to analyze this fluctuation-induced first-order transition, we should directly compute this quantity, the static susceptibility, at finite. Directly compute it at the quantum critical point and at finite Q within the double expansion and see what happens. So we find that at least to leading 2 orders in this epsilon expansion, that continuity is not ruined. And the detailed structure is as follows. So you have the tree-level term, which is just Q to the 1 plus epsilon. And you do indeed have this negative correction, but it comes with a prefactor, which is also proportional to epsilon. So if you just do, because our calculation is only valid to leading order, so 0th order and 1st order in epsilon. We should not trust the order epsilon squared terms. And within this, you see that although the correction is negative, it's actually subleading relative to what you already have at tree level. Which means that continuous transition will at least survive fluctuations, and we hope for all epsilon much smaller than 1. So of course, we have no control over the theory when we extrapolate back to epsilon equals n equals 1, which is the physical scenario. So we're not claiming that we understand, right, ultimately what happens in that case. So really you need numerics or experiments to really settle the question, which is part of the motivations. If you can search for these critical points in real experiments, we might be able to get a better handle on these phase transitions. So I want to mention that if you take epsilon back to 1, our results actually, that's not a controlled procedure, but if you do that, you get results that are consistent with the pioneering works done by these authors about almost 20 years ago. So, but there, if you naively do the extrapolation, you do find an instability. So there is some tension in these results, which we hope to be resolved in the future. So now I've talked about continuity. Let me now move on to transport. So transport has a very long and complicated history in this Hertzsprung. So the 0th order question we should ask is, why do we need counterflow? Right? Why can't we just directly do a charge transport and see, if it's a quantum critical point, you generically expect all quantities to be sensitive to quantum critical fluctuations. However, we wrote this paper, which I don't know if it's better called a gift or a curse from anomalies, which gives you some non-perturbative constraints on transporting this class of models. So let me first review some ancient lore, right, based on a calculation in the 90s done by Kim, Furusaki, Wen, and Lee, which suggested that Hertz-Miller's theory should have a singular omega to the minus 2/3 optical conductivity based on a sort of a large-n, the ordinary large-n calculation. But we know already, I think Subir already talked about this, that because of momentum drag, this lore cannot literally be correct, right? In a system that you don't explicitly break translation invariance, because a charge current always carries momentum in a system with Fermi surface, the conservation law will forbid dissipation, and you necessarily have a delta function in your conductivity. But actually, there's a stronger statement, okay? And this stronger statement can be argued both based on non-perturbative symmetry anomaly arguments, and also it's bolstered by these perturbative checks that have been performed in the last couple of years. And the claim is that the critical fluctuations don't even give you a singular correction to the Juda peak. So the conservation law only guarantees that you have a Juda peak, but you could also have an optical part of the conductivity, which is frequency dependent. But we show that if you strictly stay within the IR fixed point, that you actually do not even have these additional corrections. So you necessarily have to introduce additional operators to give you, actually, based on these perturbative calculation, at least for convex Fermi surfaces, the leading singular term in the conductivity is omega to some positive power. So it's much less singular than this omega to the minus 2/3 in the clean limit. So given this curse, let's ask, what is an escape route? Right? So there's a very simple escape route, which is counterflow. Okay? And why is that? Well, what is counterflow? So counterflow is when you have two layers and you drive currents in opposite directions. So if the two Fermi surfaces are identical, right, and the densities are the same, the two currents will actually carry 0 net momentum. So even if you drive a current, the current is allowed to decay by critical fluctuations. So at least there is no non-perturbative mechanism that forbids current dissipation. So now we can ask, if we take this bilayer or biflavor system, and we somehow have access to apply equal and opposite electric fields in the two flavors, then we will observe this particular decay process, right? So on the left, what I'm showing is the original current. You have some current running on the right in the first layer and left on the second layer. And what does the scattering process do, right? In the scattering process, the critical boson couples to the order parameter, which is C-1, C2. And see, because the boson only have small momentum fluctuations, this essentially doesn't change the momentum of the fermion. It just switches the species. So what you have is really a fermion moving, say, in the layer 1, preferentially they move towards the right. But then because of the scattering, they become a fermion moving the same direction, but now in the second layer. But if you look at the counterflow current, the destruction of this fermion in layer 1 decreases the current to the right. And the creation of this fermion in layer 2 also decreases the magnitude of the current in layer 2. So the net counterflow current after this process will indeed be reduced from before. So of course, this is just a heuristic picture, right? But this gives us some intuition because, you know, it's, if something is not forbidden from happening, then we generically should expect it to happen. And we can estimate that we'll have a natural guess for the scattering rate. And in this case, the transport scattering rate, you might guess, is just proportional to the single fermion scattering rate, because the process I'm talking about is essentially a single particle process. So, you know, you can calculate this, this diagram. This has been calculated 1,000,000 times in the literature. And you find this famous omega to the 2 over z, where z is this tunable dynamical critical exponent that I introduced. So, of course, this is a very natural result. And in fact, it's the correct scaling. But to really establish this, you need to be able to calculate all the vertex corrections, which are very non-trivial in this theory. So again, let's turn to the double expansion and see if we can say something about these vertex corrections. And here we encounter some subtlety. So the subtlety is that if we want to do transport in this double expansion, we actually encounter a surprise, which is that the unscaling of the diagrams that we calculate depend on the kinematic regime that you calculate a diagram in. So for a bosonic correlation function, I can generally divide my kinematic regime into sort of two broad categories. The first category is this so-called transport regime. So usually when we calculate resistivity, we're in the limit where Q is just equal to 0, and the frequency is kept finite. So that's the optical conductivity. But there's also a quantum critical regime where omega is much less than Q, right? For example, this Landau damped boson, the propagator for this boson has poles near omega scaling as Q to the 2 plus epsilon. So of course, this is the critical fluctuations in this theory occur in the quantum critical regime. So previously, it has been understood that if you stay within the quantum critical regime and you do calculations, right, because of this 1 over n epsilon that I talked about, you actually get finitely many diagrams at each order in 1 over n. So this renders the expansion controlled, because if you only have finitely many diagrams to calculate, you can have finitely many grad students to work on it and solve the problem. But in the transport regime, there is a completely different scenario, which is that each order in the 1 over n expansion, you actually get infinitely many diagrams. So now there's a huge challenge, which is to classify. You know, it may suggest that double expansion is not so controlled after all in the transport limit. But this is actually not the case. And so I developed this diagrammatic classification scheme in this particular expansion. And if you apply it to this problem of exciton criticality, you isolate this ladder sum. And this is just some infinite set of diagrams. But it's a controlled set of diagrams that you can analyze. And you actually reproduce the same results as if you do the same calculation in Yukawa SYK. As you know, the same structure was found in this paper by Hao Yu, also from last year. And there's a basic slogan for this classification, which you know, I won't be able to explain the details, but I wanted to sort of take away the message here, which is that the key to the classification is that I can somehow reduce every transport diagram to a specific quantum critical diagram and use the counting in one regime to do the counting in the other regime. So with this matching, then you can actually understand which diagrams are contributing at each order in the 1 over n expansion. So you can talk to me later if you want to know more details. But yeah, this is maybe not suitable for a 30-minute talk. Okay, I don't know, how much more time do I have? 5? Huh? Okay, good. So let me give a brief summary of what I've talked about so far. And let me just remind you the two main take-home messages, which is that excitonic quantum phase transitions can be continuous, at least within this particular expansion, is the perspective we've taken. But of course, we acknowledge that there's a dangerous path to small n, which is always the case. And we desperately need good numerical experiments to help us out. And the second point is that we can actually calculate in a reliable way the counterflow transport in the clean limit at these quantum critical points. And they directly encode certain universal exponents at these phase transitions. So there's a generalization. I wasn't sure if I had time to get to it, but I'll flash one slide on this, which is that you can also consider an analogous problem where the excitons are not made of electron-hole pairs, but composite fermion and composite hole pairs. So this kind of setup can be embedded in the conjugate term band setup that Chao Ming talked about in his talk. So here, let me just remind you briefly, what you have is a term 1 band, let's say, and a term -1 band, and both of them are half-filled. And you can go into the state called conjugate composite Fermi liquid, where essentially both layers form a composite Fermi liquid, but with some additional interlayer interactions that change the universality class of this state. And starting with this parent state, what you can do is you can condense the composite fermion exciton, right? But the composite fermion exciton is not gauge invariant. As we know, the composite fermions each couple to an emergent gauge field in each of the two layers. So this exciton will carry some gauge charge under one of the gauge fields. So what happens is that you Higgs one of the gauge field, and the remaining gauge field couples to a neutral Fermi surface. So this kind of state is familiar in the spin liquid literature. And this can that's what we call the exciton insulator star. And this state is a gapless candidate for the fractional quantum spin Hall effect, but I won't discuss this in much detail. But following the framework that we developed earlier, you can consider an excitonic QCP of the composite fermions. So actually, this excitonic QCP involves many more degrees of freedom. You have Fermi surface coupled to gapless bosons, and they're themselves coupled to these emergent gauge fields. But actually, the double expansion that I talked about generalizes easily to this case. And you can still control the theory, and the counterflow resistivity still takes the same scaling form. Although I want to emphasize that the dynamical exponent here need not be the same as in the fermionic, the physical electron example. So, yeah, some future directions. One natural generalization is to think about multi-layer transport in non-Fermi liquids, and whether or not, because so far what we talked about is this critical point where you have two species of Fermi surfaces interacting strongly with each other. You can also think about a case where you bring some weakly interacting layer close to a strongly interacting layer, and see if counterflow transport can get around the usual problems that we have with momentum conservation. Yeah, and another interesting possibility is that so far I've assumed that there's some symmetry that exchanges the two flavors, but this symmetry may well be broken, right? In the particular setup in TMD systems, the conjugate term bands, actually their band structures, their Fermi surfaces do not match with each other. So these valley, the Fermi surface in valley K and the Fermi surface in valley K prime have some mismatch. And when you have a mismatch, the generic scenario is actually something like this, right? Where the Fermi surfaces they will intersect at some finitely many points. So this is reminiscent of the hotspot models that show up in these finite Q ordering transitions like antiferromagnetism or charge density waves. But there are some important differences in this case, especially because there's some important differences, but we hope that at least in the limits where the mismatch is weak, we can still solve this using the method that was developed by Schlief, Luntz, and Sunsik in 2017, where they solved the antiferromagnetic quantum critical point. And finally, it's an interesting question to ask whether you can incorporate spatial disorder into this controlled expansion. And yeah, that's a completely open question that I'll just leave to the future. So, okay, I'm done, but yeah, thanks for listening.
I might have missed it. Does your model has U1 cross U1 symmetry, so that the charges are conserved in each layer?
Yes. Yes.
Doesn't that also imply that the this counterflow current should also be conserved quantity if you have U1 cross U1?
Not quite. Yeah.
So what breaks that? Like why?
Yeah, it's. Yeah.
You're saying like the momentum of one layer is not conserved.
No.
Okay.
What's conserved is the sum of the momentum.
Okay.
Yeah.
That's the only conserved quantity, and it's orthogonal to that, so that makes a difference.
Yeah.
And the fact that charge in each layer is conserved separately doesn't really change that because you can still exchange momentum.
Yes.
I see.
Yeah. That's the picture I was drawing, which is essentially exchanging momentum between the two layers.
Thank you.
Yeah.
Sorry, just to follow up on that, like, so a single Fermi surface has like a emergent conserved charge for each point of a Fermi surface.
Yes.
So if you have two layers, naively you would, and you're not allowing any hopping between them, naively you would say that there's one conserved quantity for each charge on each Fermi surface. Is that not enough to protect this counterflow current? Or is that symmetry broken somehow?
I think you would have to consider, for each theta, you would have to consider the charges on the two layers as a whole, rather than they shouldn't be individually conserved at the critical point.
But I thought you're saying that there is no hopping between them, so then why would they not be individually conserved?
There's no hopping, but at the critical point, right, there's a critical boson, which is like a fluctuating hopping term that scatters C dagger 1 to C2. So,
okay.
Yeah, I haven't thought very carefully about, if you think in terms of the full LE1 symmetry, how to interpret this result. But from the controlled expansion, if we just don't think about the emergent, just directly do the calculation in the controlled expansion, this is the result we find, which seems to suggest that there's nothing. And this doesn't depend on like Fermi surface shape or whatever. It's a generic property.
So I also have a question. In your calculation, you got this omega to the -2/z just from a self-energy diagram? And
No.
Oh.
Yeah. Good point. Maybe this is to be clarified. So this is a natural guess, but this is not what I actually did.
Okay.
Because what you actually do is you have to compute all these higher order diagrams.
And the vertex corrections do something to it.
Yeah, they do something
They change the prefactor.
Yeah, they change it, yeah.
Okay.
Yeah, I like to ask very basic question. So you calculated this counterflow resistivity and so on. So in order to measure those quantities, in principle, you apply voltage on one layer and measure current on same layer or different layer or something like that.
Yeah, so in this case, I guess one way you can do it is to apply opposite voltage on the two layers, and then just measure how the current decays.
I see.
Yeah. But it's not always layer, right? That's the thing.
Yeah.
So this Excitonic, for general flavor index, it's hard to, experimentally, it may be hard to couple to that order parameter. But there are these spin-resolved transport measurements that maybe you can dream of, but I'm not sure. Maybe experimentalists can say whether they can do it.
Thank you.
Any further questions?
I remember in our calculation of this omega minus 2/3 behavior, it's maybe omega 2/3 behavior. That's basically for the quasi-particle lifetime. And however, if you think about the Fermi surface fluctuation, the result is that it's indistinguishable with the Fermi liquid theory. So there's a situation because there's a mode. It's a gauge field mode, based on forward scattering. It may destroy quasi-particle, but the collective smooth fluctuation from your surface don't see this kind of scattering. So then it's almost like this effect is not there, so it's just Fermi liquid-like. That seems also what you said. I try to say the constraint from anomaly seems also say that even if you think the transport property, just the Fermi surface dynamics, then it's you don't see this short lifetime effect.
Yeah, so I think these statements are related, but they're not quite exactly the same.
Okay.
Because, so in the old calculation that you guys did, you have an interpretation of the scattering rate, the transport scattering rate. Instead of being omega to the 2/3, it becomes omega to the 4/3. And because of that omega to the 4/3, if you put it in a denominator and you expand, there's a Judah peak, and then there's a correction, which is proportional to 1 over omega to the 2/3. It's,
okay.
yeah, so that's the procedure that you can do. But here we are making a much stronger statement.
Okay.
Not just us, the number of groups that have corroborated this, which is that even the omega to the 4/3 term is not there.
Oh, I see.
Yeah.
Okay.
At least in the clean limit.
Yeah, sure.
So normally I would say that in order for a current to be well defined, the charge should be conserved. But here you have the situation where you want to say the interlayer charges are not conserved, but then you still want to describe the intralayer current, so is it really well defined?
No, the charge is conserved. So I do have U1 cross U1 symmetry. So there is a separate U1 in each layer, right?
I thought you said the boson is going to scatter between...
Yeah, but the boson itself is also charged under one of the U1s. So yeah, there's actually a boson contribution to the connectivity. Maybe that's what you're asking about, but that's subleading relative to the fermion contribution. Yeah. There's no, the UV symmetry, yeah, maybe I should have emphasized this, it's just U1 times U1 for the two layers or two flavors. And you spontaneously break one of them when you go across the transition. Yeah.
So once in this boson condensed phase, I assume you don't have diagonal U1 anymore. And then how should I think about counterflow experiment, which essentially is probing the response of this diagonal U1?
Sorry, you don't have, the spin U1. Yeah, so it's a superfluid for the spin U1. Yeah.
Then you do counterflow, where essentially applying that spin HU.
Yes. Yeah, so that's why I'm not doing it in a phase. I'm doing it in the quantum critical fan above the critical point. Yeah, that's why it's everything I've said applies to the sort of the critical regime. Yeah. But of course, I should mention that, as I think Chenghao and Stefan talked about in their experimental talks, that exciton fluctuations could potentially enhance superconductivity. And there are a number of theory groups that investigated that possibility. So if there's a dome on top of this, then it's not clear if this physics will be visible before the TC sort of sets in and kills everything. Yeah.
So if you fix epsilon to be small but non-zero,
small but non-zero.
Can you still say the transition is continuous, or?
No, because the expansion requires, so you mean take epsilon to be small but non-zero, but n to be finite, or?
Keeping n times epsilon to be fixed, order of 1.
Then it's probably fine. Yeah.
I see.
At least, so okay. Of course, higher order things could ruin this, but to the order that we're able to calculate, it is continuous at small epsilon.
Okay.
Yeah. But eventually, I don't know. I don't even know if the small epsilon fixed point is connected to the epsilon equals 1 fixed point. So.
I guess there are no further questions. So let's thank Darius once again.